briefly to introduce this small genome. And using mitochondrial DNA as an example, these small molecules only contain 37 genes, but all of those genes are necessary. And we can divide these genes into 2 ribosome RNAs, 22 tRNAs, and altogether with another 100 proteins encoded by the genomic DNA, we can form this mitochondrial-specific translation system. And the main purpose for this mitochondrial-specific translation system is helping the 13 mRNA encoded by mitochondrial DNA. And all these coding products are located at the core parts of these different complexes of the oxidative phosphorylation, except the complex 2. And here I use the complex 1 as an example. In total, 45 different subunits from this complex 1, and 7 of them are encoded by the mitochondrial DNA. And in the past several decades, the mitochondrial DNA mutations increased during the natural aging has already been widely found. And also the famous repeated mouse, which can generate it, which has increased the point mutations and can mimic very well the aging phenotype, also confirm those random point mutations can contribute to the aging process. But what we are interested in is the single point mutation in terms of how does these single point mutations come from, either from this maternally inherited or the de novo generated during early embryogenesis. And as I just mentioned before, actually these single point mutations can cause completely different cell response if they located at distinct genes in the mitochondrial DNA. So how does these single point mutations change during aging, and what's the consequence currently is far from known? And why do we care about this single point mutation? Here I would like to tell you actually those single point mutations can cause a lot of mitochondrial diseases in the clinics, affecting multiple organs, and the human prevalence is 1 out of 5,000. It's not that rare, but also not very popular. But nowadays, more than 700 of these point mutations has already been found can correlate with mitochondrial diseases, and among the 100 has already been confirmed with pathogenesis, with different kind of biochemical way. And those mitochondrial diseases is very complicated in terms of they have varied clinical phenotypes. They can occur at multiple ages, affecting multiple organs, and sometimes is unpredictable. During the in vivo pathogenesis is very complicated, so till now it's lack of specific therapy. So why does this class of the disease very complicated? It's mainly contributed by this multiple copy nature of the mitochondrial DNA within one individual cells. So, so for the individual somatic cell, normally has several hundreds to several thousand copies of mitochondrial DNA, and for individual oocyte, it has the most abundant mitochondrial DNA inside. It contains more than 200,000 copies. And for the sperm, it's less than 100 copies for individual cell. And this brings another layer of complexity, is that all the genotypes of this mitochondrial DNA, if they are identical within one single cell, we can call this as a homoplasmic situation. But actually, most of the case, and all of us, actually, we are heteroplasmic level. That means within our bodies or within individual cells, actually, they could coexist with the wild type and also the mutant mitochondrial DNA. And since this is very heterogeneous, since almost all of us are heteroplasmic situation, and also these heteroplasmic situations could be changed during different processes, such as during aging or during maternal transmission. So our research focus is one to address whether during the aging, whether these single point mutations were changed. And to address these questions before 2020 is extremely difficult because we didn't have enough mouse models that can mimic the animal models can mimic with single point mutations can mimic human patients because the lack of enough useful tools to edit mitochondrial DNA. But since 2020, some great tools has already been developed. in terms of they can, now the editing mitochondrial DNA becomes possible. So here I listed 3 main different kind of editing system, and use D3 as an example. I would like to tell you, actually the principle of this editing system is purely protein-based, and independent of the CRISPR-Cas9 system. And once this editing protein is imported into the mitochondria, they can initiate or they can generate the new mutations that did not exist initially before. And with this powerful tool, we want to generate different kinds of mitochondrial DNA mutations and to answer the interesting questions we raised before. And here is I want to briefly introduce the workflow in our lab. So basically, we're looking for the very important and conserved sites from the human patients, and then we optimize the editing system in the mouse cells and validate the pathogenicity. Here, we use ND1 point mutation conducted in our lab as an example. So from here, you can see clearly, actually, this ND1 point mutation can severely affect the convex 1 assembly. So it's very pathogenic one, also in the mouse cells. And after that, we will conduct the mouse editing to generate multiple mouse tools with heterogenic mutation load and for the research. And from here you can see, once we got the editing parts, we isolated mitochondrial DNA from the tails or the toes, or even ear cut, and then for the NGS sequencing, and use very simple mathematical way, we could define the mouse genotype as a mutation node. And from here you can see, actually this editing system is really powerful, can supply us with a lot of mouse models with direct mutation nodes. So after we got this editing parts, we dissect each mouse model and to check the mutation node from different organs to compare with their own tail mutation node, which we have already confirmed that is very stable during aging. And then this normalized organ mutation node can really tell us whether they were the different organs, the mutation node, whether they were changed during aging. And from this picture, you can clearly see actually we trace those mice for as long as 2 years, but for multiple organs, the ND1 mutations stay very stable. So then we also we want to check whether they have certain kind of mutation change during the maternal transmission. We intensively intercross those mutant mice with Y-type males, and then to record all the pups mutation loads, and then plot into this diagram. And from here, you can see actually, if I use the 35 mutant mom as an example, all the pups from these 35 mutant moms, the mutation load is significantly lower than the mother itself. This is a very strong sign of the purified selection. That means this selection occurred during this ND1 maternal transmission. And this is consistent with what has been reported before, that actually selection is always shaping the human mitochondrial DNA transmission, even in the healthy populations. And our model is a very good model to study these purified selection mechanisms. And after that, once we check the mom's age when they give birth, and very interesting findings is that we found actually during the mother's aging process, actually the pups mutation load start to decrease. What does it mean? It means in the aged mom, actually they can give birth to low mutant pups. And this is, and we then check because the oocyte has the genetic device for the maternal transmission, all of these mitochondrial DNA. So then we check the oocytes from different females, and also confirmed that the aging enhanced purified selection actually has already occurred, already finished in this mutual oocyte. And this phenomenon actually is contradictory to traditional thinking about negative effects from aging, because all we know before is that as mother's age increases, we can transmit more mutation to next generations. But for these certain point mutations, we see the opposite. So then we ask, when does this selection occur? Purified selection occurs. So here, allow me to briefly introduce the whole oocyte development stage. We can briefly separate this into two stages. One is the prenatal, another one is the postnatal development. And here I want to say, actually, once the female are born, all the oocyte number has already been determined in the neonatals. And during the lifetime, the early stage of the oocyte residue in these primordial follicles, they will be mature and develop into the neutral oocyte all the time. And the most important thing is during this postnatal nutrition process, actually, as these diameters of the oocyte expansion, the mtDNA copy number within this oocyte also increased from several thousand to several hundred thousand. It's almost 100 times more than its original status. So then, since the maternal aging effect must be occurred during the postnatal nutrition, we systematically check multiple stages of the mutation node of the multiple stages after birth. And firstly, we check the newborn female pups, and then the average mutation node for those mutations is very similar to their mothers. But then we figure out when the mutant moms, once they achieve to certain mutation node, like more than 37%, the selection has already occurred. But this data is not extend the maternal aging effect, but really we can really say this is the result of this prenatal oogenesis process. And after that, we also check the different young age and old age females at these primordial follicles. And what we found out, the maternal aging effect actually did not occur in this early stage. Why we so emphasize this primordial follicle, the early oocytes? Because this is the only long-lived cell type within all different developing oocytes. And once it got activated, it will go one-way maturation process. Either undergoes decoding, or they can usually into the oocyte. So here we would just like to see, we see actually for this early oocyte, we didn't see the selection happen. But for the antral oocyte, the antral oocyte is the later stage, very close to the maturation completion. And what we see is the strong purified selection already finished and very close to the N2, and the mutual oocyte we detected before. That means actually this selection stage is between the primordial follicle and antral follicles. So then we make, based on this analysis, we make a small conclusion that we do see two waves of selection. One is during the embryogenesis, another one is during this oocyte mutation process after birth. And then these two waves are distinct in terms of the first wave is mutation node dependent and also much more moderate compared with the second wave. But since we have already seen since the unique feature of the oocyte development postnatally, we further divide the second wave of selection into two stages, including the sensing stage and also the conducting stage. So the conducting stage is mainly responsible to generate the selection force, but the sensing stage is for accumulating the aging effects. And so the strong purified selection of our mutant mouse well common. Another paper published several years ago, they claimed that in the early stage, in the primordial follicles, there is almost no complex 1 exists. And they also claim that there is no selection of the complex 1 mutations. And here we would like to say, actually, they indeed has complex 1. They indeed should have complex 1. Otherwise, they could not accumulate this aging effect during the aging effect for the purified selection. So then we want to know whether this specific phenomenon is only unique specific point mutation in MD1, or is broadly can be widely adopted in other mutations. So then we want to we choose another point mutation that which is completely distinct from the MD1 point mutations. And we choose one mutation in MD5, which is located in a very far away from MD1 in terms of this convex 1 structure. And then this molecular pathogenesis is also completely different. And this point mutation is responsible for the proton pump. It's not affecting the convex 1 assembly. And most importantly, this MD5 point mutation can cause a lot of patients in the clinics. And then we generate another mouse model and trace the selection pattern. And what we see is during the maternal age enhancing selection also occurred in this point mutation. And if you compare with MD1 selection strands, we would like to see, we could see actually for this MD5 mutation alone, the selection strands much weaker. And this probably is one kind of explanation why we could have more MD5 mutations in clinics than MD1 mutation. So let me make a small summary. And we utilizing these different animal models and find actually the purified selection can act on these convex 1 related mutations. And also the maternal age can enhance this selection. And most importantly, we define the postnatal selection occurs. And this didn't have been clearly shown before. And then what's the molecular, how does this selection happen? When we talk about selection, there must be some kind of condition. So we want to ask which kind of level of selection occurred, either at mitochondrial level or it's at the cellular level through this cellular condition. And then think about we check all the oocyte mutation load in the age and compare with the young the starting pool of the early oocytes. And from here, I would like to convince you that in the aged females, they can ovulate Y-type oocyte in terms of there is no mutations inside. And then those, if you trace it back, there is almost no Y-type early oocyte in the starting pool. And meantime, when we check the selection strands, actually this is totally independent of the mother's mutation load. It means the selection unit must be small. So these all together let us think about the selection occurring must at the mitochondrial level. So that I want to introduce some very important work contributed by other mitochondrial genetics researchers working in this field before. They utilize the different, they use like one important drosophila lines and claim that actually the selection could two main force to shape this selection. Either is preferred replicate Y-type mitochondrial gene, but either the two main mechanisms who contribute this selection. Either the Y-type got more chance to be replicated, or the damage can be actively eliminated. So this one is still under debate. So we would like to know what's the mechanism for our mutant mouse model. And since we have already defined the selection stage, but this stage is extremely difficult to study in terms of they cannot be controlled, and then they are very present in the whole ovary section. So that we use another way to capture this developing oocyte to compare. We utilize the stereoscope, which has tried to use transform changes with the spatial sequencing, and then with this powerful technique, we can capture from different ovaries the same development stage of the oocyte and compare their transcriptome changes. And the top changes, the differentiated gene jumped to our analysis is that both cytosol or mitochondrial ribosome proteins, they show this upregulated in our mutant of developing oocytes. And for sure, of course, this translation pathway is also the top one significant can change the pathways in the mutant developing oocyte. So then we wonder, because it looks like the mutant oocyte activated the translation activity. So we thought, since mTOR pathway is heavily involved in these translations, heavily involved or control this translation capacity within the cells, we thought probably this mTOR pathway or mTOR activity got upregulated in the mutant oocytes. And indeed, yes, we validate that these mutants can increase the mTOR activity. And then once we use rapamycin to inhibit the mTOR capacity, we significantly reduce the translating activity. Meantime, we also reduce the strength of the selection enhanced by the maternal age. So, at the meantime, we also check whether we have actively elimination of the damaged mitochondria in these developing oocytes. And we use multiple ways, but we could not find very strong evidence to support that the damaged mitochondria can be eliminated during this process. So in the end, we also propose, and our data also suggests that the wild type, probably because the wild type mitochondria can got more chance to be replicated. So this is cause of the selection occurred. So then let's take a step back to see how this process got occurred. And we want to say, actually, during the aging process, we speculate that in the early primordial oocytes, and the aging can increase the disparity between the healthy and the damaged mitochondria, and consequently, they would change the whole environment. For example, increase the mTOR or translation capacity. And once we use the rapamycin to inhibit or to make those early oocytes as well as the developing oocytes more present, this selection disappears. So here I would like to make a small summary that we want to say the selection occurs in this complex one related mutation occurred at mitochondrial level, and increased protein translation is necessary. And here I would like to say, because rapamycin now is a famous drug, which can be proposed can delay the aging and as well as the maternal aging. Actually, we can see using this drug can also reduce the strength of purified selection. Probably this is a course for when we utilize these chemicals to delay aging. And our work also has some implications for clinical and basic research. Currently, the maternal age haven't been considered as the effective factor for translation those single point mutations. And our data suggests definitely the maternal age should be included and should be counted. And also for basic science, if we want to generate high mutant mouse models to mimic the human diseases, we should bring those the models as young as possible. And we hope in the near future we can change with more detailed mechanisms findings. We can change the somatic stable mutant level into the purified selection style. Then they can help us to develop new therapeutics for mitochondrial disease in the future. And here, also, I want to spend 1 minute to introduce another mouse model generated in our lab that is located in the mitochondrial TRNA mutations. And these mutations is completely different from what I introduced for the complex related mutations. And interestingly, this mutation we found PB can specifically accumulate this mutation during aging, and of course, very severe mitochondrial diseases at the old age. And we found very interesting mitosausage or mega-mito pathogenicity in the epithelial cells in these mutant mouse models. And if you are interested in this part, you can go to post 48. My students will be very happy to share with you about their interesting findings. And in the end, I would like to thank my co-lab and also Westlake families, as well as my collaborators, and thank you for attention.